Good morning, everyone, and welcome to this Spotlight Talk. I'm Giorgio Veronesi, President of the European Federation of Chemical Engineering, EFCE. I've been in the board of EFCE in various positions for over 9 years, and currently I'm in my second term as president. I'm a chemical engineer by training, graduated in Padua, Italy, and I've been spending the whole of my career in the engineering and construction business, involved in many projects, mainly abroad, with several assignments overseas. I'm very happy to be involved in the introduction of this webinar on powder technology for sustainable production of battery electrodes, a very important subject these days, which combines comminution classification as well as mechanics of particulate solids concepts. And I'm really looking forward to participating to it. Let me say something about the Spotlight Talks series. This is now our 6th year of the Spotlight Talk initiative, which started in 2020 to keep together the chemical engineering community during the COVID pandemic. The success of the initiative convinced us to transform the Spotlight Talks in a regular feature of EFC program. So now we have one Spotlight Talk series in odd years, like this 2025, and two in even years. This spring, 11 of our working parties and sections, chemical engineering applied to medicine, sustainability, chemical reaction engineering, process intensification, comminution classification, mechanics of particulate solids, the two ones represented today, fluid separation, polymer reaction engineering, static electricity, crystallization, early career chemical engineers are delivering over 2 weeks 10 webinars with talks on specific topics by leading industrial and academic experts. The complete program is available on EFC website. EFC promotes scientific collaboration and supports the work of chemical engineers in 27 European countries, representing more than 100,000 across Europe. EFC working parties and sections cover all major specific aspects of chemical engineering and are in fact at the core of the organization, forming the scientific engine that drives many of EFC activities. They provide an important forum for technical exchange and networking among chemical engineers in Europe and abroad. Before concluding, I would like to thank all the people who work hard inside the working parties, the sections, and the EFC in general for this initiative to happen and be successful. In particular, many thanks to EFC Martin Pou in Toulouse, who did most of the conceptual setting up and practical activities. She's here even today. And I'm taking this opportunity to inform you that the EFC board has decided to award to Martin the prestigious Dieter Behrens Medal for her contribution to chemical engineering that will be delivered at the European Conference in Lisbon in September. So thanks, Martin, and congratulations for this well-deserved award, an important recognition for your work. So I thank you for your attention. I wish all the speakers and the attendees a fruitful and successful webinar. I would then give the word to the chair of the Working Party Mechanics of Particulate Solids, Professor Diego Barletta, for the introduction of the works and the program today. Diego, the floor is yours.
Thank you very much, Giorgio, for the nice introduction. So I'm Diego Barletta. I'm an associate professor of chemical engineering at the University of Salerno. And today I'm here as a chair of the working party of mechanics of particulate solids. So let me give an introduction on the topic. So today we will discuss the relevance of powder technology to the sustainable production of battery electrodes. Batteries are fundamentals to various technologies, serving as energy storage solution for portable electronics, transportation and green scale system. And common cell format include cylindrical cells that are often used in application requiring robust design, prismatic cell, which feature a rectangular form factor allowing for efficient space utilization, and pouch cell, known for their lightweight and flexible packaging, enabling customized design. Now, among various battery technologies, lithium-ion batteries have garnered significant interest due to their high energy density and extended cycle life, making them suitable for numerous applications, particularly in portable electronics and electric vehicles. The fundamental operation of LIBs relies on the reversible movement of lithium ions between the anode and the cathode. Let's have a look at the structure of the battery compartment at its main component. The primary anode material is graphite, typically with a particle size around 20 microns, exhibiting a layered structure that facilitates lithium-ion intercalation. Silicon, with nanoscale particle forms below 150 nanometer, is explored as a high-capacity alternative. Common cathode materials include lithium nickel manganese cobalt oxide, NMC, often with particle size around 500 nanometer, known for its high energy density, and lithium iron phosphate, which can have varying particulate forms, including nanorods of 30-50 nanometer or larger particles around 3 microns, valid for its safety and cycle life. Now, the conductive additives are incorporated also to enhance the electrical conductivity within the electrodes. Carbon black forms a conductive network consisting of spherical aggregates with primary particle size ranging from 10 to 500 nanometer. Carbon nanotubes, one-dimensional nanomaterials with diameters of 0.5 80 nanometer and lengths of 5 to 20 micrometer, provide efficient electron transport pathways. Binders are essential for maintaining the structural integrity of the electrodes. Polyvinylidene fluoride, with particle size typically in the range 150-300 nanometers, is commonly used in cathodes due to its electrochemical stability. For anodes, especially in aqueous processing, carboxymethylcellulose, CMC, a macron-sized powder, serves as a binder and dispersant, often used in conjunction with styrene butadiene rubber, SBR, which exists as a milky white liquid emulsion with particle size around 150 nanometer, to enhance adhesion and to the current collector. The liquid electrolyte, instead, is a solution of lithium salts in organic solvents that facilitates lithium-ion transport between the electrodes. It also contributes to the formation of the solid electrolyte interface layer on the anode. So, in conclusion, the particulate form of this battery component, including their size, shape, and distribution, is a critical factor influencing the overall performance and efficiency of lithium-ion batteries. The increasing adoption of electric vehicles is driving a significant surge in the demand for raw materials essential for the battery production, including lithium, nickel, and cobalt. Minimizing the carbon dioxide impact associated with the extraction and processing of this material is crucial for the sustainability of electric vehicles. Furthermore, addressing the social aspects of raw material sourcing, such as labor practices and community impacts, is paramount for ethical production. I'm sorry for that. 1 second. It was too fast in clicking. Okay, that's it. The development of circular economy for batteries necessitates research and development in particle technologies across various stages. Mechanical recycling of end-of-life batteries and production scrap by optimizing physical processes for efficient material recovery, hydrometallurgical treatment and reconditioning of spent active material by developing environmentally benign chemical processes for metal extraction and reuse, synthesis of active material and passive materials by tailoring particulate properties for enhanced battery performance through an energy efficiency synthesis methods, raw material handling and mechanics by addressing challenges in powder flow and processing for consistent electrode manufacturing, energy efficiency production of tailored electrodes by developing advanced slurry processing and dry coating technologies for uniform and high-performing electrodes with reduced energy consumption. So today we will shed light on some of these aspects of particle technology that are relevant to this type of production. And so we have a program of 3 talks. The first will be given by Professor Arno Kwade on powder technology-based innovation of modern battery electrode production. The second by Professor Rachel Smith on linking process, structure, and performance for lithium for ion battery electrodes. And the third one by Dr. Hans Schneider on key processing steps in dry battery electrode production, dry mixing, and powder handling for film formation. After each presentation, we will have some time for questions. The audience cannot pose the question directly, but they can write the question in the Q&A box during the session, and we will convey the question. So it is my pleasure now to give the floor to Professor Arno Kwade for the first speech.
Yeah, thank you very much, Diego. Thank you, Giorgio, for the really great introduction and also explaining already the structure of lithium-ion batteries. And I will try to share my screen so that I can start. So I'm, as Diego said, a professor at the university in Braunschweig, and I'm heading the Institute for Particle Technology since more than 20 years now. And already in 2007, I was approached by the industry if I can help them for the production of lithium-ion battery cells, especially regarding the mixing process, but also regarding calendaring and coating process. So that, you know, I started, let's say, to go into this field and also have a lot of scientific work done since then. Today, I want to talk about the powder technology and how this can help to drive innovations in modern battery electrode production, by that giving also an overview about what is happening in this field. You have already seen the structure of lithium-ion batteries with the anode, the cathode, and what is important to say is that this structure is very important for the performance of the battery cells. And I think especially Rachel will talk about that later on in detail. But to say that you can see that the porosity or the pore distribution, the distribution of the binder and carbon blacks within the electrode, they are very decisive for the electrode conductivity. And also for the ionic conductivity. Both have to be in a several range so that the cell at the end has a good performance regarding fast charging, for example, but also energy density and so on. And also lifetime, what is, for example, mechanical and adhesion strength is a factor for that. So here are some of these, let's say, quality values like energy and power density, lifetime, safety, sustainability, what we already addressed, and costs. These are all goals which we have to achieve for modern and innovative electrode production. In Braunschweig, we are running several labs for this purpose. We started with a big lab in 2014 as a joint lab, and we are working together with, or I'm working together with 17 other PIs from different fields, from electrochemistry, from electrical engineering, up to, for example, economics. And we are working on the entire topics and having this great production lab with a dry room, which is very decisive or important for producing battery cells. We also have a diagnosis lab where we dismantle cells and have a closer look what happens during operation of the cell. We have a new circular lab where we operate a recycling plant and have no large facilities also for electrode production. And we will start an education lab for our students, but also for industry. And all that along this very important circular production, we call it. And you see what already Diego has shown, that there's a lot of potential for chemical engineering in the material synthesis, in the electrode production itself, but especially also in the recycling field. Now coming to my talk in detail, after the introduction, I will come to how we can improve the state-of-the-art electrode production, and then I will skip or go over to the dry electrode production, which is also the topic of our third presentation in detail before I come to a conclusion and an outlook. Let's start with the state-of-the-art electrode production. And this is shown here. You see that we have the materials, the raw materials, and they are first have to be maybe pre-treated, but at least dry and for sure wet mixed. Then they are coated on a substrate, what you have just seen in the figure. It's out of copper or aluminum on the cathode side, copper on the anode side. And then we have to dry the slurry in a, let's say, state-of-the-art process. Then they are calendered. Calendered means they are pressed down to a certain porosity. And then we have to transfer them into the dry room because the electrolyte is very sensitive to moisture. So the electrodes have to be dried, and then we can package them. We can contact all the different electrodes because there are more electrodes in a cell, what also have been shown by Diego at the first figure. And then we have to close or, let's say, package these electrodes into a case, which can be hard case or it can be pouch. And then we have to fill it by the electrolyte, which is very sensitive to moisture, what I said. And then at the end, we have to formate. So formation is something like starting up the cell, which is also very critical for the later performance before we have the last quality control and we can sell the cells. And if we now look for the energy consumption of the different process steps, I mean, then you can see that the most let's say, or the highest energy consumption is in the coating and drying, especially the drying step. So it's about 40%. You can find also some other values, but they are still in the range of 30 to 50% for coating and drying. And then also the post-drying needs some energy, and also the operation of the dry room. You see that these are very crucial steps, especially also for the sustainability. So that we also focus on the steps a lot. Going a little bit deeper in the process structure and performance relationships, we can have a closer look into the electrode, and you see the electrode can have a certain thickness, it can have a certain density and porosity, mechanical strength, wetting behavior by the electrolyte, and this all is important for the later performance, and it all depends on the particles itself, but also on the microstructure of our electrode. And this can also be seen here because, for example, due to the structure and also the distribution of the carbon additives and also the binder, you get a certain conductivity, electronic conductivity, but also at the end ionic conductivity. And so that this micro nanostructures determine the electron and ionic transport, and the ratio will show nice results about that, also regarding simulation. And they are key to enhance the energy and power density. Now coming to the process of electrode production, what I just said, we have a dry mixing, a wet mixing, a coating and drying, and a calendering step. And so maybe we have first a look on our quality parameters, maybe the direct structure parameters along the process chain. First of all, for the dry powder mixing and also the wet suspension, then at the end we can measure the particle sizes, the particle morphologies as a disperse, let's say, parameter. And for the later electrode, we can measure the pore network structure, so pore size distribution, for example. We can determine the tortuosity. The tortuosity is the length of, let's say, a path through your electrode for the ions. And this should be as short as possible. And also we, for example, determine the inner carbon black porosity as an important parameter for the structure. And by that, you can come then to performance parameters. So that means electrical resistance, powder flowability, maybe for the intermediate powder. We can have the viscosity and stability of our suspension. This is more for handling powder in suspension. And then we come to the electrode properties like electrical and ionic conductivity, adhesion force, especially also for handling the electrodes during further production. And then at the end to the capacity, C-rate capability, fast charging capability, etc. of the cells. So now, first focusing on dry and wet mixing, we have the, let's say, task, to disperse the conductive additives, and I will focus here on carbon black, but today CNTs, carbon nanotubes, are almost always inside also the electrodes, and also this is very crucial, they're dispersing. And this carbon black determines, beside also the CNT, the microstructure of the electrodes. And we need, like it's shown here by the green line, a good electronic cardback. We need good ionic transport through the pores and also through the pores of the carbon black. And it also determines the deformation behavior and mechanical integrity, and by that also lifetime, but also production properties of the electrodes. And that we have to have a really intensive focus of this carbon black binder network, which is between the active material particles, which are shown here as a cathode particles, polydispersed particles. Today also we use so-called single particles besides this polydispersed particles, which is only, let's say, one particle. It's not an agglomerate like the typical polydispersed ones, but this is a topic which we maybe don't focus on too much today. As I said, the inner carbon black porosity we found is a good measure also for the structure. It also is the case that the smaller the agglomerates, the smaller also the inner porosity, because the agglomerates break where the porosity is the largest. And we could calculate this inner carbon black porosity using normal mercury intrusion measurements. And then from that, we could calculate that. And we could also show that the ionic resistance really depends, as you can see here, on this carbon black porosity. And there's a minimum in resistance, which means an optimum at a certain carbon black inner porosity. And you see the same here for the capacity loss of the cell at different C rates. So I think it was from, let's say, almost 0.1 C up to 3 C. 3 C means that you load your cell 3 times an hour. And if you have 0.1 C, then it takes 10 hours to charge the cell. So if you have fast charging, then that gets important that the conductivity is in the right order. But we are looking for another parameter which we can use also for quality control during the processing, especially already during the dispersing of the particles. And it's not so easy because you have bimodal distributions of the carbon black. I mean, the active material, they shouldn't change. Then you have a degradation of them. But so that we have to measure the carbon black. So we defined a way to measure the carbon black distributions by some centrifugation and certain laser diffraction measurements. And you see then this very strong bimodal distribution. So at the beginning, you have a lot of agglomerates of the carbon black, and with increasing dispersing, these agglomerates are dispersed to aggregates, very close, strong aggregates. So they are shifted in this direction. For really high dispersing, almost no agglomerates exist anymore, and we have only aggregates on the left side. But it's not the goal. I will show it later, to have only aggregates because we need some small range and also long range conductivity. So there should be a good mixture of aggregates and agglomerates in our suspension for the later performance of the cell. And we're looking for one parameter which can be used as a measure or a characteristics of this performance. And we found that, let's say, the enveloping surface of the aggregates is a good measure for that. And we can estimate or can find a characteristic value for that if we calculate the relative amount of aggregates. That means what is this area under the left curve here on the left side compared to the entire curve, and what is the median diameter of the aggregate. So we multiply the amount by the specific surface of these aggregates, and by that we get a measure we call the dispersion index. And now I want to show how this dispersion index is affected by the dry and wet mixing process. First of all, the dry mixing process, we use usually high intensity dry mixing devices, and we try to coat more or less the active material with the carbon black. That can be done very intensively. That is here on the right side. But it can also be very loose. That is here shown on the left side, where we have only a rotary drum mixer. If we have a, let's say, high intensity mixer, then the agglomerates are much smaller. Already the first aggregates are sitting on the surface of the active material particles, and we do it in an extreme case. Then we really coat the active material particles by the carbon black, what is maybe too extreme, but you can see also later. So something in between is what we need at the end. And if we have this dry premixing compared to without premixing, what is shown here. So if we have the black curve, that means there's no premixing. Then we start at a certain dispersion index, and we can reach after 60 minutes about 3. But if we have a certain premixing, you see that we start at a much higher dispersion index, or we have it already after 50 minutes, let's say this way. So it's much more effective than the wet process. And also we can reach much higher values, at least in a, let's say, recent time. And this is due to the disagglomeration of the carbon black agglomerates to aggregates. And for example, if we have an optimum dispersion index of about 3.2, 3.3, you can see that we can reach this with a nice dry premixing by less than 15 minutes. If we have no premixing, then we need 60 minutes. So that's, but economically wise, you have to decide, what is more important, having another process step, or let's say taking much more time for the wet dispersing process. For the wet dispersing, typically you use planetary mixers, which are out, let's say, since they started to produce lithium-ion batteries. And they are, let's say, 90% of the gigafactories in the world today. But there are also others. There are other solutions, and the most promising one is an extrusion. Extrusion is a continuous process. We don't have several batches. We can also operate at much higher viscosity. So you see here we have a viscosity up to 10,000 Pascal, but we can also go up to 100,000 Pascal with an extrusion process. And the mean residence time can be very short, but also helps, especially if there might be some side reactions. But we have to control this process very nicely because we can't change anything after the product left the machine. Now, what happens in the machine is, if you look into the screw design, is that we stress the particles due to shear inside the suspension, and we can measure or describe that by the so-called stress intensity, which is nothing less here than the shear stress inside our extrusion machine. And as a measure of that, we can use the torque or the specific torque of the machine. Besides that, we have to see how often such particles are stressed, at least in the volumes where we have really high stress intensity, especially where these two screws are coming together. And if we multiply both, then we have a measure for the specific energy input into the process. And what we can see is if we have low stress intensity, then we have still a higher number of agglomerates, lower number of aggregates. And if we increase the stress intensity with the same comminution or dispersing time, then we have lower and also smaller agglomerates, lower amount and also smaller size of agglomerates, but we have much more aggregates which are formed here. And now going to the next slide where we can show that if we increase also the concentration of our particles, that means we have a high viscosity, very high viscosity within the extrusion, and we have some kneading blocks normally in the extruder installed, then you can see that the dispersion index increases a lot. And we have a really high torque, which then decreases again. The decrease is due to especially the delamination also of the graphite particles. So we have a degradation, which we don't want to see. We can also have this with smaller concentration, but it's really a little bit only. And if we now look for the results, you can see that the results with high kneading, but only 58% of concentration, that gives us very good or relatively good performance results. That means a high capacity, even at high or let's say reasonable high C rates. 1 C means charging the cell in 1 hour. If you go to half an hour, then it decreases and so on. But this can also be changed, for example, by the thickness of the electrode or by using more carbon black and CNTs and so on. This is something what the companies have to do to find the right performance data. Now we have the next step is coating and drying. It's also a lot can be done there, especially also to avoid migration, so that binder and carbon black goes to the surface of the electrode. But due to time, I cannot go into detail here. Also, we do a lot of work in this direction. And then there is coming the calendering process, which also is very interesting. Also there we have done a lot of work. I want to show here only one result. Before I go to the dry coating, this calendering is a really mechanical compaction of the electrode, let's say to come from freeways between the particles to smaller streets and to also have less volume for the same capacity. So that means we can increase electrode density, and also by that, the overall energy density. We can improve charge transfer, especially the electronic transfer. The ionic transfer gets worse usually. Improves the mechanical behavior. The electrode gets much more elastic, and that's really good for handling. We can smooth the surface, control the thickness, and that we do by the force which is coming here from this roller, which is acting on the electrodes. And Rachel will also talk about it a little bit later more. And but there's also elastic recovery, as you maybe know that from tableting. And this elastic recovery also is, let's say, hindering our calendering process. And one single result I want to show you here, because it relates also to what I showed you regarding the dispersion or comminution process, is that the dispersing of the carbon black is really also decisive for the calendering process. That means for small dispersion indexes where we have a lot of agglomerates, the line load is much higher to come to the final result. It's especially due to the elastic recovery, which is much higher. Then we go down to a smaller line load at a dispersion index of about 4. And if we increase the dispersion index, have only aggregates almost, then we need again a higher line load, which is against, let's say, the elastic recovery, so that we come to the final density, in this case of 3.2 gram per cubic meter. Okay, this was some insights into the production of wet produced electrodes. And now I would like to come to the second topic of my talk. It's about the dry electrode production. And as I said, we have to go for a more sustainable production of electrodes. And one measure or one possibility is to change from wet to dry coating, or we call it also semi-dry. I will show you how that works. And this also shortens the process chain. So we have a more or less dry mixing. We have then the dosing of the powder and the film formation, and no drying and no calendering, because the film formation is, you will see it later, also at the same time, the calendering process. So we have a relative short process chain. We also can avoid critical solvents because, for example, for the cathode material, we need NMP as a solvent to work with PVDF as a binder. We have a much higher energy efficiency, so minus 30% of the overall energy consumption. You have seen 40% was for the coating and drying, but now we need only 10% instead of 40. And also the CO2 footprint is getting much better. We have a cost reduction, and especially also the buildings can be much smaller. In the moment, for a coating line, you need a building which has a length of about 100 meters, so really big buildings. And this can be much shortened, maybe to 10 meters by the dry coating process. And we have also no migration anymore. To maybe start with the semi-dry coating process, that is something we developed at our university, also patented it. Here we produce by the extrusion process, not a suspension. We really produce granules, which are soft and deformable. Here's a small video where you can see the cutting of our extrusion strengths. And this gives us then nice granules, which will be shown here, which then we dose onto a calendering machine. And on the calendering machine, we can then form a nice thin film with really good properties. And you can see here different ways to process our active materials and conductive additives with a normal kneading screw, with an intensive kneading screw. You see here we have more kneading elements in the screw, or with a normal planetary or dissolver process. And this also changes the structure, because with a high intensity kneading process, we also delaminate the graphite, which we don't do in the reference, and also almost not with the normal kneading screw. And at the end, if we come to the performance, you see that the only kneading screw gives us the best results. So we're very pleased with that with this new process, we get really good performance. And we have a more homogeneous electrode, because that is here shown here. This migration is not taking place. Usually during drying, the solvent has to go out of the electrode. By that, it takes carbon black and binder with it to the surface, so that at the end you have a concentrated binder carbon black amount on the surface of the electrode, and less in the bottom where you need it. And this is not the case if we have the semi-dry process. But it's also not the case if we have a full dry process, which I show here. In that we have again a mixing process, but in this case a full dry mixing process. In the in the semi-dry process we have still some solvent. It's much less than saturated, so it's maybe 50% of the pores are filled with liquid. Here we have no liquid, and we have to mix the process, but we have to use a certain binder. I come to this, otherwise it doesn't work, to get a really nice mechanical strength of the electrode. It has to be fed then into, for example, a calendering machine, which is the most common production way today, but I will show you a little bit later also other possibilities. And then you form the film, and usually you have to go through several rolls to come to the final the density and also final thickness of your electrode, and then you laminate that on an electrode. So it sounds simple, but it's not that simple because a lot of parameters affecting this process. One is the mixing process. We can do it again in a dry process with high intensity mixers from Zeppelin, for example, which you will see later, or we can also do that with an extrusion process, like I have shown for the semi-dry processing. But I want not to focus on that today more. I want focus more on the film building and the effect of the particles. Maybe one word as a comparison to the wet process. Here you see a surface of a wet processed electrode. You see that we have this carbon black binder domain, which is really at the connecting points between the particles. And if we know, and this is a more bridge-like, connections, particle bridges we have. If we go to this dry coating, we have this PTFE, which forms nice fibrils, so particles which are really high aspect ratio. And these fibrils, which you can see here really nicely, they connect our particles and also the particles with the carbon black. So it's more a spider web-like domain. And the fibrillation of the PTFE depends a lot on the mixing process. For example, in extrusion, you can have much smaller and shorter fibrils if you want. In a dry or a batch process, usually they are a little bit larger. But there's also, again, an optimum of length and thickness of this PTFE fibers. Now, this mixing process, as I just said, especially decides or shows the binder fibrillation and determines the binder fibrillation and also structures the carbon black. And it's important to say that in this case, the dry process has to do everything. There's no wet process, as I have shown before. What is then can do more work and you can finalize your structure. That has to be done here really during the dry processing. And this has then a crucial effect on the coating, but also on the later electrode performance. Here today, I want to show you a comparison of different materials, so how we can process graphite, LFP, and NCM. We also published that already in powder technology, how these particle structures, sizes, also densities affect at the end the fibrillation and the final electrode properties. And you see that here the NCM is in the size of almost 10 micron. LFP is a poly-dispersed LFP, so it's even a little bit larger or coarser. And then we have the graphite, in this case also even a little bit coarser again. And we use some carbon black for an anode, it's 1.5%. For the cathode, it's 3%. And in any cases, we had 2% of PTFE. And now there's the mixing process. We had first an starting homogenization of our material at, let's say, high also intensities with high power input kilowatts. So it's the power input. Then there's a, let's say, softening phase, and then we come to the fibrillation. So here we add the PTFE, and then we have the first fibrillation of the PTFE, and we take a sample. We have another 10 minutes fibrillation, and afterwards we take sample 4. And then we have a cooling down period without mixing. And then we have a final homogenization at lower temperatures for have the final powder properties. And what happens regarding the size distribution, for example, here the graphite, you see at the beginning without PTFE, there's not changing a lot. It shouldn't be that there's a change, but after adding the PTFE, fibrils formed, and this formed fibrils then also form agglomerates or granulates inside the mixture. This is seen here. And with increasing fibrillation, there's a, let's say, increase in the granulation size and also amount. And after the final homogenization, these granules are again decreased because they have been too big. And also the amount is a little bit smaller. So we also detached already graphite again from the fibers. Maybe also looking here for the LFP, it is same, no change in the particle size distribution. Then we have really a lot of big granules after starting the fibrillation, and also you see really big granulates still after end of fibrillation process. But then for the final homogenization, we come again to smaller granules, which we need for the coating process, and it's a little bit more granules, but also finer material. So these are the original primary particles which are not granulated, and these are the granules. So we have a mixture out of, let's say, free particles and particles which are detached which are sitting on the fibrils. So these are then for the NMC, it's the same. It was very similar to the LFP. And you see that with the graphite, the PTFE slides more than its fibrillates, because graphite, it's, have a really low friction. And LFP, there's a fine particle content, which is still there also after fibrillation. And we have a fast process here also for the NMC. What happens now with the properties of our powder, and you see, for example, the bulk porosity first increases after fibrillation because you get agglomerates. You can think about that, and after further fibrillation, it changes a little bit, maybe decreases slightly, but there's no big change anymore. In the compaction speed of such a tapped density measurement, you see that after fibrillation, because we have this high porosity, the compaction speed increases a lot, but then decreases a lot, but then because there is already, or it's more fluffy, and after we have more fibrillation, it stays almost, or in case of NMC, it increases again. Now coming to the dosing process, which is also shown by, or will be shown by Hans Schneider. And you see we have maybe a pre-meter dosing, what is not so typical today, but it's also direct roller feeling, which is the most common ones. And what I wanted to show you here is that we have a two-roll calendaring process. For if we dose it onto the conductive collector, or we have the several steps through the calendaring machine. And I think there are two production processes which are typical. That's the Maxwell process, where we have a freestanding film or roll connected film, and we need several steps, to come to the right thickness, and then we transfer it onto a substrate. And there's another dry tech process where we have a high differential speed of the rollers, and by that we come down to very thin layers already, and then we can directly connect it to, or laminate it to the collector. And to show that how that looks like, you have the powder here, you get a sheet, and by several, or in this time 3 densification steps, we get a nice film, which is really mechanical stable and can be then transferred further. The question is how we can describe that. That can be the process by the powder flow abilities and also by the uniaxial compression. And you see that the powder flowability is different, especially the wall friction angle is much lower for the graphite, and that helps that we only need one step to produce the electrode. With LFP and NCM, you see we have much higher wall friction angles, but there's some differences in the flowability, but that is not so decisive. But the wall friction angle is decisive, so that we need 3 steps here to get the right thickness of the electrode. Also, what can be seen here, here's 1 step, all is fine. Here we need 3 steps to come to the thickness below 100 micrometer. A much better measure is the uniaxial compression. And what I want to show here very shortly is that with this measurement, you can predict almost, if you know the line load in the calendaring machine, what is later on the porosity of your layer. What is shown here, my computer is very slow in the moment, but you can maybe see where the straight line goes down. That is what we get at the end. Now coming to the conclusion, I hope I could show you that we have material, process, structure, property function, which are really decisive for the later performance of the cells. We need energy and cost-efficient production processes. We have to model and predict also the, let's say, work or the perform or the input of the conductive additive structure. And what also Rachel will show, we should develop digital twins of the process, but also how the structure determines the later performance. And very important, what Hans will show is the handling and dosing of the dry powders for the semi-dry and the dry processing of all our electrodes. And I think there are a lot more topics also for chemical engineers. That is the synthesis of the particles. I think we can do so much there in this field. Then is also, if we come to the solid state electrolytes and solid state batteries, we have no liquid electrolyte anymore. So even more particles and even more mixing, and the structure is important. And also the recycling process. Here you see our recycling plant is very, let's say, chemical engineering research. So a lot to do for us. And by that, I want to thank all my co-workers who are working in this field. And thank you also to you for your attention. And now I'm open for questions.
Thank you very much, Arno, for this excellent presentation, very wide, with a lot of information and details. And so we have time for question. We have one from Vincent Finzi, that is, in your semi-dry process, which solvent are you using? And do you still have to remove the solvent after the calendering process?
That's an excellent question. So in our process today, we mainly use not water, but we can also use water, but ethanol or water-ethanol mixture. And then we have to dry out this material. That's correct. I was a little bit too fast maybe at that point. But we can dry it in the calendering process. So if we use heated calendering rolls, it is sufficient at least to, let's say, up to 10 meters per minute to dry the electrodes. If we go faster, then maybe we have to use some infrared or something measures. But it's also possible to use electrolyte solvents. So, for example, DC, so that you don't have to dry the electrodes, but then you really have to do everything in a dry room. So you have to coat that in a dry room. It should stay in the dry room because all the electrode itself after the production or even the processing itself is already very moisture sensitive. So these are advantages and disadvantages. So we look for both, and I know that there's also an US startup company, let's say, which also doing it with a electrolyte solvent to try that as an plasticizer, let's say, for the dry processing. Yeah.
Thank you very much. So apparently there are no other questions for the time being. So I think we can move on with the program. And so now it's the turn of Professor Rachel Smith. So it's my pleasure. Rachel, the floor is yours.
Thank you very much. I'll just share my slides. Okay, is that can you see all that well?
Yes, we can.
Yes.
Wonderful. Thank you so much. So today I'm going to be speaking a bit about a subset of what Arno was speaking about, and we're going to focus in primarily on the calendaring process in the electromanufacturing process. So, and not only are we going to talk about the calendaring process, but we're going to be linking the process with the final structure that we are generating, and then that structure with the performance of the electrodes. So, I'm speaking today, I'm the work package 1 leader of a project called Nextrode, which is short for Next Generation Electrodes. And this is a project sponsored by the Faraday Institution. It covers a broad range of manufacturing technologies for the electrode manufacturing process, but mostly limited to lithium-ion batteries for our project. That said, we try to keep the research that we do as applicable outside of lithium-ion as possible. So what we're trying to do really is understand the physics that are occurring in the manufacturing processes at a quite a generalizable level, and then be able to apply that understanding to lithium-ion batteries, but there's no reason it couldn't be applied to other types of battery manufacturing, right? It's all basically physics and chemistry. So as I said, this is a collaboration between four different universities. We have the University of Oxford, we have obviously the University of Sheffield, where I'm based, we have the University of Birmingham, and we have the University of Warwick. And we have five primary work packages. Work package 1 is called cooperative particles, and that's where we are trying to understand the particle level interactions that are occurring in manufacturing electrodes, and also the particle level effects on electrode performance. We also have people at Birmingham working on mixing metrology, and what they're trying to understand is how can we start to measure and quantify these mixing processes that Arno spoke about so well earlier. We have work package 3, which is called smart structured electrodes, and that's trying to look at novel ways to make new electrodes. We're doing some of that in work package 1 as well. There's a bit of an overlap there, but we're coming at it from different perspectives. We also have image-based modeling, and you're going to see some of the results from the image-based modeling today. And then we have digital manufacturing, and that's really important. So this is trying to understand taking all the learnings that we're taking across the project, but making it much more digestible and usable by industry by trying to distill the important information using things like machine learning. And so I'll be covering some work that we've been doing collaboratively across these work packages today. So the work package 1 that I was speaking about, we have cooperative particles. We're looking at lots of different angles on the particles that make up an electrode. And as Arno spoke about earlier, we have there's 3 primary ingredients, you could say, in an electrode. Now, I'm not saying there's only 3 ingredients. There's lots of other things that go into an electrode that sometimes, depending on what you're trying to achieve. But the main ones are we need the active particles, which store and release the ions of interest, and in this case, it's lithium. We have the carbon or other conductive material, right? So it's often carbon, but not always. And what that does is conduct the electrons throughout the battery electrode. And then, of course, we have a binder, and that binder needs to join all the particles together. When the electrode eventually goes into a battery, of course, we have the electrolyte, okay? And the electrolyte is what the ions travel through to get between all the different active particles. So we're looking at this from lots of different scales. So at the bottom scale, we're looking at particle scale design. And this is where we're trying to look at, can we make particles that will work better in an electrode from a particle scale, from an individual particle scale? And some of that is about, can we make effectively the correct mixtures and the correct structures that will make the downstream processing much easier for us of electrodes? And that's looking at doing this for both dry electrode manufacturing, which Arno spoke about towards the end of his talk, and also the traditional wet electrode manufacturing when we make a slurry. We then also are looking at this conductive binder domain, the CBD domain, phase design. And we know, and I'll show you later, it's incredibly important. This CBD is very, very important in the way electrode performs. So we're trying to see if we can understand the way that CBD affects the performance, and then say, okay, well, how can we design that CBD to be what we want it to be, basically? And Arno's already spoken about some of that, about trying to disperse, for example, the conductive particles in different ways in order to improve the electrode functionality at the end. But what I'm going to speak to you mostly about today is this final point, which is particulate modeling of electrode calendaring and the CBD phase. And so this is where we're trying to model the process or model elements of manufacturing of electrodes using traditional particle modeling techniques, for example, DEM simulations, to help us understand the relationship between the manufacturing process, and then the microstructure of the electrode, okay? And then I'm also going to go on and show how we've applied that to then predict the electrode performance. So if I take us through, now I'm going to do this very briefly, just a reminder. This is a very basic breakdown of the electrode manufacturing process in a standard slurry process where we mix all the particles into a slurry. So here we have our dry powder mixing, which is not always, you don't always have this in every process, but as Arno mentioned, it can be very beneficial occasionally to do that. You then take that into the wet powder mixing, so then we add our powders and turn it into a slurry with a solvent. We coat that onto a film. We then dry that film, and as everybody knows, that's quite expensive, drying that solvent off. And then we go through this calendaring process, and this calendaring process is effectively a compaction step. As Arno discussed, we're taking what is a relatively porous structure and we're reducing that porosity. Now, that has a lot of, that's very important. Reducing that porosity is very important for us. And the reason for that is that it brings all the active particles, it makes the distances between the active particles smaller. So we're making it easier for the ions, potentially reducing the distance that the ions have to travel, not necessarily. But a really big thing is that we're bringing the carbon or the other conductive particles closer together. And what that means is that it's easier also for the electrons to travel through the electrode. So we know that basically if we have high calendaring levels that can improve the volumetric energy density, but it does increase the diffusive resistance. So what that means is that as we squish the electrode, we're making it, in some ways, we're making it harder for the lithium ions to travel through the electrode because we're reducing the space available for the electrolyte, and we're increasing the tortuosity. So Arno spoke a bit about the tortuosity earlier. So we have this sort of balance here where we need to balance the improved energy density, but we will increase the diffusive resistance. So how does the microstructure evolve during calendaring? Well, you can see here we've got electron micrographs at all different scales of an electrode. These large particles here, these particles here are NMC, nickel, manganese, cobalt particles. They're the active particles in the electrode. And here we have what we call the CBD phase, right? So this is the carbon binder phase. And you can see it's a very porous structure, right? And the structure of this phase is really, really important to the electrode performance, as I said. And here we have an example. We've got an as-cast, so this is without calendaring electrode, and this is a slice through, and we're grateful to Yiga Sung from Oxford University who provided these micrographs. And you can see basically we have this CBD phase here. It's quite porous, and then as we calendar it, ideally what we're doing is we're squishing this CBD phase and not affecting the active particles too much. Now, you can see here that, of course, we are affecting the active particles a little bit, and that's to a certain extent, you want to minimize that, but you certainly want to minimize the breakage of these particles, but it is very challenging to not have any break. The pressures that you're using and the stress through the plane of the electrode is difficult to achieve the calendar that you want without breaking any particles. But that said, we want to try and minimize that sort of effect. The main reason that we're doing it is to squish up this CBD phase and bring the active particles closer together. Now, a lot of people anyone who knows about DEM would look at these particles, these round or these spherical particles, and think, wow, that doesn't look too bad for DEM. So anyone who's not familiar with DEM is a method, discrete element method. It's a method of modeling particle motion and particle forces, basically. So it's used quite a lot in process industries. It's used in comminution. It's used in granulation, lots of different industries. And it's also used in tableting for the pharmaceutical industry. And so we and other authors, Arno has done some work himself in looking at this, have thought it's a good case for us to use DEM simulations here to understand how does the calendaring process affect the microstructure of my electrode. So the don't worry about the equations here. I just wanted to show that in essence, it's actually a very simple modeling technique. What we're trying to do is we're tracking the particle positions with time. We add forces, and we're looking at how does that force affect the individual particles, how do they move, and we model this using two things. They've got basically the force between the particle interaction forces and then bond forces. So without going into too much detail, we're looking at the deformation of the binder phase between the primary particles, as well as effectively the forces between the active particles when they come into contact directly. So in order to apply this technique, we first have to understand what structures do we have at the beginning. So we used tomography scans basically to take. We found some very nice databases. To start with, we used original databases of scans of electrodes. And then we turn that basically, we segment the image, we turn that into a binary image, and then eventually what we do is we replace each of the particles in our tomography scan with a spherical particle. Now the reason for that is because spherical particles are by far the easiest type of particle to use in DEM simulations, but we're not relying on that. I'll show you a little bit later how we've also double checked our assumption that that is okay. And what we do then is we say, okay, we've got a tomography scan of a pre-calendared electrode, and we've got a tomography scan of a post-calendared electrode, and we see that change in the microstructure. So we captured that here by using the porosity of the structure that we have. And so we ran simulations, and what we found was we got quite reasonable agreement here between the porosity of the structures and the compaction pressure in the electrodes. Now, of course, we need to do some. We have to do some calibration here, right? So some of the parameters in the DEM simulation are not well known. So we have to do calibration here. But what we find is that if we can then keep those parameters constant across all the different compaction pressures, and this is the result here basically. So we're quite confident now that our model is giving us a good result. The other good thing that we can find from these DEM simulations, of course, is that not only can we study the compaction of the entire electrode, but we can understand the stresses, individual stresses at very small scale within the electrode. So in the future, the idea is that we will be able to use this to help us predict whether particles are going to break or not under different compaction loads, which is quite difficult, to be honest. It's quite difficult to predict without doing any kind of simulation, because it's difficult to predict the individual stresses inside this 3D structure. So that's something we're quite interested to do in the future. So what we can do here is we can study we've got all these different, we've effectively made all these different structures with different porosities, and we can look at, okay, what is the minimum path length in different directions? And that minimum path length is really, really important for understanding our lithium ion transport. So how is it going to be able to transport around these particles? As I said, as we compact the electrode, typically our lithium ion transport becomes more difficult. And we can also look at interparticle gap size distribution. And one of the beauties of this type of technique is that we can study a whole range of different things. We can also look at what we call tortuosity. And as Arno said, tortuosity is looking at how difficult is it effectively. What we're trying to understand. So tortuosity is looking at the tortuosity, like how winding basically are the paths through the porous structure. The reason that we're so interested in it is that we're interested in this lithium ion transport, right? So basically the lithium ion has to travel through those tortuous paths. The interesting thing here is that as you compact electrode, we need the electrodes to go through the through plane direction, right? When we compact the electrode, we change the through plane direction of the tortuosity in a different way to the in plane direction. And so that's also really important to capture. And this is a demonstration that we can capture basically this quite well. So now we've gone through and we've basically validated a way to understand the structure of an electrode going through the calendaring process. And obviously we haven't done this for lots of different materials, so we've done it for an individual case, but we've got reasonable confidence with that case now. But the next level, of course, is understanding, well, how does that affect my electrochemical performance? This structure only matters insofar as I'm capturing the performance of the electrode. So we've proposed this digitized workflow and published this in 2023. And basically what we're trying to do is create a workflow for people to follow, including us, which looks at the way we can benchmark or compare our model with our simulation, and basically validate our model. And so here we have our physical methodology. We create our electrode, we compress it, we characterize it, the structure of it using X-ray CT, and then we do electrical chemical testing. That basically gives us performance. But when we do our virtual, we can do our X-ray CT and import that in here. So also do like E-compression, look at our structural evolution, do our electrochemical testing simulations, and then do that comparison, basically. So we have here, I did mention earlier that we did double check. So we're making this sphere approximation. Now this works really well for some things, but it doesn't work great for everything. We had a good feeling it would work well for these particles, these NMC particles, because they're quite spherical. But we wanted to make sure. So we took that tomography scans and we basically said, okay, let's say they're all spheres, and then let's say they're all ellipsoids instead. And the ellipsoid obviously has that degree of freedom that you can change the aspect ratio. So we replaced each of the particles with ellipsoids and DEM, and then we ran our DEM again. And what we basically found was that when we replaced our particles with our ellipsoids, if we go and look, for example, at our pore volume, so basically this is our pore distribution here, what we find is that actually the spheres do a better job for us in this case than the ellipsoid approximations. So now there's not too much difference in it. It's quite close. But that said, we found that basically the spheres work better for us, and we're very happy to hold on to that. And that was validating for our methods, basically. Now I mentioned electrochemical analysis. Now this is a tool that's been used for a number of years. We work together with our friends at UCL and Oxford on this technique. And basically what this means is if we have the structure of an electrode using existing methods, finite element analysis methods, we can predict the electrochemical performance of these structures. So we wanted to double check, because we're taking a tomographic scan and turning that into spheres, we wanted to check, okay, how does that change the state of lithiation or voltage, for example, in an electrode? So we took out these ones here on the right are our tomographic scans, and then on the left we have our ideal or our spherical scans, basically our spherical approximations, basically. And what we wanted to do was look at so when we run our simulations of the electrochemical performance, how does that affect the performance that we're getting? And what we find here is that for our ideal case, which is the red dots, and that's talking about spheres, we get very similar mean values to what we get for the tomography basis, right? So you can see the red and the blue here are in reasonable agreement. But what we found is that, yes, they're in reasonable agreement, but actually we get much more scatter with the real shape of particles than we do with the spheres, and that is to be expected. By using non-spherical particles, you effectively get hotspots of activity or inactivity, basically, because of the shape of the particle and the way the lithium travels inside the particle. So what we found was that you get, on a microstructure scale, you do get some variation between our simulations, but on average, if you're looking at the performance of the electrode, and you can see this here on the cell voltage level, we're getting almost identical results. And so that was very good. We're able to acknowledge that we're not going to capture the distribution, for example, of the state of lithiation inside the electrode, but overall we can capture the general behavior. And then, of course, we can look and see we've got different calendaring levels here. We can look at the state of lithiation between calendared and uncalendared electrodes. And of course, as you might expect, and this has been demonstrated, as we calendar our electrodes, what we do is we bring that distribution of our lithiation in tighter. So an uncalendared electrode, we have a much larger distribution. When you calendar it, you bring that distribution in tighter, basically. So, when we look at our carbon binder domain characterization, though, we see that the micropores basically, we have macropores and we have micropores, and we know that these are very, very important. So understanding the contribution of the micropores and the macropores to the electrode performance is really, really important. And so we came up with an idea to try to basically, rather than when we try to do our electrochemical simulation, we should look at how important are these micropores to the performance of the electrodes. And of course, we can do that digitally because we can use algorithms to create these micropores of the CBD structure inside the electrode, and we can change the relative amounts of micro and macropores while keeping the same total porosity the same. So we have that power with the computer. So we looked at experimental data here. So these dotted lines here, experimental data, and the simulation data are the squares. And what we attempted to do is create bimodal distributions, basically, of micropores and macropores. Now you can see that these aren't perfect replicates, basically, and what we're seeing here is that we're overestimating, I guess, the sharpness of these peaks in our simulations. But we're not too worried about that because what we're trying to do is, rather than trying to perfectly replicate experimental data, we're trying to investigate the role of this microporosity. And to be honest, it's not too bad when you think about it. The simulations, the agreement between the experimental and the simulated data is not too big. So we increased our microporosity, and what we found was that when we increase our microporosity, we massively increase our specific capacity under certain conditions. And so this was a really important finding. What we found is that, and what this means is that if in manufacturing we can change our microporosity inside the electrode, we can start to really control the electrode performance, or we at least influence it substantially without changing, without putting more active particles in there. And that's the important thing here, is that we're trying to not have to have too much more active particle in there. That's the expensive part of electrode in terms of the materials, is very much the active particles that store and release the lithium. Now we come to our machine learning framework, and the whole point of this is that X-ray tomography is very, very expensive to do experimentally. Making electrodes is expensive to do experimentally. Sadly, DEM simulations, which we have been using, is expensive to do computationally. What we want to do is not have to run our simulations every time to generate a huge data set. We want to be able to use machine learning to be able to understand all the different effects of the different parameters so that we can design electrodes without having to run thousands of simulations and thousands of experiments with thousands of CT scans. And so we've started working in this area, and this is working with our friends at Warwick. So in order to do this work, we had to generate quite a lot of different structures, but we only did about 45 DEM simulations. So that's probably about 6 months of simulations, I would say. And the idea for doing this is then, as I said, to effectively have a model that can predict almost any condition within the boundaries of what we have simulated, okay? So we created, I'm going to go through this reasonably quickly because of time, but we tried to vary many different parameters. We varied the distribution of the particles. So here we have, on the left, we have our original distribution, and this is basically a replicate of the particle size distribution of experimental particles that we had. We then deliberately, by maintaining the same average particle size, but we deliberately manipulated that distribution to give us a bimodal distribution, so that we have a lot of small particles and we have some big particles. And then we also then deliberately manipulated that to give us a much tighter unimodal distribution. So all the particles are close to there's not a big variation in the particle size. We also changed our cumulative pore volume fraction. So we looked at, so basically calendaring to different levels. And we changed our bimodal pore, we changed our pore size distribution. So we changed basically the fraction of the pores that are taken up with the micropores as opposed to the macropores. And so we did all these manipulations. And then we also looked at the thickness of the electrode, which is known to be a very strong, have a very strong effect on performance of the electrodes, especially at high C rates, at higher power draw, basically. So by doing a machine learning analysis, and we use a gradient boosting machine learning algorithm called XGBoost, we're able to then see what are all the relative contributions to the performance of our electrodes. So for example, here you can see we're looking at our impact on the electroconductivity. On the right, we're looking at an impact on tortuosity. So what we found was that by the calendaring level by far had the largest impact on our conductivity. The microporosity had quite a substantial effect on our conductivity, and interestingly, the particle size distribution didn't have a huge effect. Now we know that the active particles don't participate too much in the conductivity, and it's much more about the conductive particles that are controlling that. But at the same time, I was a little surprised to see such a small effect of the particle size distribution because of the effect of that on the pores in the electrode. And similarly, we can then look at that impact on tortuosity. And in this case, we're using tortuosity as a way to think about the ion transport within the electrode. So when we do our electrochemical results, we typically run our simulations, and we're looking we're looking at things like, so the state of lithiation, for example, in our lithium ion electrode. So this is just a snapshot of some of the data that we found here. So you can see when we have we have very thin electrodes run at really low power draw, basically, which is low C rate, low current. What we find is that the state of lithiation is high. Basically, all the electrode is lithiated. When we get to much higher C rates with a thin electrode, what we find is that some of it is lithiated, but some of it is very highly lithiated, and some of it is very poorly lithiated. And this happens for almost all electrodes. As we increase the power, we basically reduce our capacity. We reduce the ability of the electrode to be able to release and store those ions away from the current collector, and that's a known effect. And we can also capture this as we go to thick electrodes. So these are the simulations where the electrodes are much thicker. And what we see, even for low C rates, we get poor lithiation here. So, and as we get closer to the current collector, we get much better lithiation. As we go for a thick electrode at high C rate, of course, we get very, very poor lithiation across the entire electrode. And so what we're then trying to do is understand, okay, can we capture the battery capacity? And what we find is that as and the beauty of this machine learning analysis is that it allows us to effectively understand the contributions of all these different factors. If we understand the contributions, then we can start to try to design electrodes for a specific performance, and that's really important. Every battery has desired performance targets. A car often needs, if you want to have a high performance esports car, it needs high power. It has high power requirements. You need to be able to get that energy out really quickly. That's different to the battery in my computer, which doesn't need that high power relative to that car. So we have here we're looking at all these different variations. So we're looking at microporosity, our particle size distribution, our calendaring level, and our thickness. And the important thing here is that we're able to quantify the contributions of each of these towards our electrode performance. So here we've got this digitized workflow of the process basically that using the process to develop the microstructure and then using the microstructure to develop performance. And we've used the machine learning tools to help us understand this whole relationship even better. But the next step for us is to start solving this inverse problem. So that means we want to be able to design, we want model-driven design. Now the machine learning approach is one part of this equation. But the machine learning is still working in the forward direction. So by using machine learning, we can basically populate very large. We can use the surrogate model that we've developed in the machine learning approach to populate very large data sets, basically of process structure performance. But then we need to start solving that inverse problem using optimization methods, basically. So for us, that's one of the next things we're really excited to do is start challenging ourselves to say, okay, if I want a certain performance, how do I generate that? What structure do I need? What process do I need to generate that structure? So in conclusion, there's substantial challenges for the manufacture of electrodes, as Arno has brought up, and but there's really exciting opportunities here, I think, for improved process efficiency, reduced cost, and improved product quality. And I'd just like to say a big thank you to all my research group. This is a little bit of an old photo, so some of these guys have moved on and some new faces have turned up. But very much they are the heart and soul of the group. Thank you.
Thank you very much, Rachel, for this very interesting insight. So we have time for some questions. There are from the audience. Okay. So there is the first one by Jonathan Meyer asking, are there potential applications for using flow sheet modeling to determine how draw mixing parameter could influence downstream processes, such as calendaring?
Yeah, that's a really good question, Jonathan. I think there's huge opportunities for us to do this in the same way as it's been done for other industries like the pharmaceutical, foods, agrochemicals, things like that. So I think there's really good opportunities to do this, but we don't yet have the science, I think, to be able to do this very well. I think it's being developed by researchers around the world, like Arno, like us. But I think we're all working on this sort of work. But that would be the aim of the game. Basically, would be able to do this without having to do a lot of experiments.
Thank you. So there is another one by Amok Barla. Are the carbon black binder types generalized for modeling? Because there are different possible binders that are presently used. Are they all being approximated as spherical particles for the simulation, even though they can have different interaction mechanisms?
Yeah, so in this case, the carbon binder domain, rather than being represented by particles, is represented by bond models. And that's really important, and it is one of the drawbacks of this. Is basically because carbon black particles are typically nano-sized, it would be incredibly computationally intensive to try to simulate those in DEM. We have tried a few different techniques to simulate the CBD phase using DEM. So one of the things you can do is you can coarse grain it. Of course, you can create particles maybe that are 1 micron in size or 500 nanometers in size, and sort of try to do it that way. But what we've done so far is rather than doing that, we've used the bond model and we've calibrated the bond model against the calendaring data that we have. So what that means is we're using a model that the Edinburgh elastoplastic model, which allows us to look at elastically deforming plastically deforming binder between the particles. Does that make sense?
Yes, absolutely.
Yeah.
Thanks. And then one from Aparna Parakad Unikishan. How did you evaluate the CBD in DDM, especially its property? What size did you use?
Yeah, so the CBD, as I said, so when we're doing the DEM, we know what space is occupied by the CBD from the tomography. We don't know the size of it's very difficult to resolve the size of the particles. We do use things like MIP to understand the pore space inside the electrode, if that makes sense. So we can see the pore size distribution inside the electrode. But in the DEM, we are using a bond model that we've calibrated against experimental data. And because that experimental data is so expensive to generate, that's one of the reasons we're interested in the machine learning process.
Thank you. And the final one from an anonymous attendant. In the calendaring process, is the frictional interaction, the roller and the feed materials, an important factor? If so, how was this considered in your DM model?
Yes, and so the frictional interaction between the roller and the feed materials is an important factor, and the importance of that factor varies strongly with the materials that are going through the calendar. And we did not consider that in a strong fashion here. So we obviously have an interaction between the particles between the roller and the feed. We've set that as a typical typical properties basically for I think we used, I can't quite recall, I think we used steel for the plates, and of course you also have we have to not forget, if you have a one-sided calendar, if you have a one-sided calendar, basically one of the interactions is actually between the foil. If you have a double-sided film or one-sided film, so you have to think carefully, are you doing a single-sided film or are you doing a double-sided film? But in effect, this is something we haven't included a lot yet. It's something we're aware of, and we've been talking a lot with the DEM software providers about how we can better understand that, because effectively the interaction between the roller and the surface of the material can create more of a stretching effect than what we have captured here in our DEM.
Yeah, thank you very much. We have another question, but maybe you may want to reply by writing directly, because we have, I think, to follow the schedule. And so
we are coming back to the final discussion, I guess. Giorgio. You are muted.
Yeah. I think we are a bit, we have overrun a little bit, but I would say that the participation was quite good. And even now that we are about 10 minutes later scheduled, still a lot of people are attending. So this is a clear indication that your webinar was very interesting for the audience. So I would like to thank you for your contribution, and I think that I'm sharing the opinion of all the people who have attended this very interesting and very informative webinar. Thank you so much, and don't forget to promote the next Spotlight Talks. So we have a very busy calendar and still a lot of interesting subjects for this week. Thank you.
Thank you so much.
thank you.
Oh, thank you.
Thank you.
Bye.
You.
Thank you, Martin, as
Bye.
usual, for
Thank
the
you.
organization.
Thank you. Bye-bye.
Bye-bye.
Thank you.